So sitting on the table in front of me today is just this absolute mountain of research. I mean, we are looking at a massive stack of sources here.
It is, it's quite the pile, yeah.
Right. And it ranges from like historical pandemic data all the way to really cutting edge CRISPR research. And looking at all this, I realized something. Growing up, I had this very, and I think you listening probably had this too, this very simplistic view of
Oh,
medicine.
absolutely. The whole, transactional model of health.
Exactly. It's so linear. You get sick, you go to a doctor, they look at you, figure out what's broken, hand you a pill in a little orange bottle, and then boom, you're
Right,
fixed.
like a mechanic fixing a car.
Yeah. But the mission of our deep dive today is to completely shatter that illusion for you. We want to shortcut your path to understanding how modern medicine is actually, well, it's a massive, deeply interdisciplinary web of sciences.
And it's a web that is actively tackling humanity's biggest existential threats.
Mm-hmm.
I mean, we're talking about cancer, global pandemics, failing organs.
Right.
You don't fight those things with just a stethoscope and a notepad. It requires blending biology, physics, chemistry, and honestly, high-level engineering.
Which is wild to think about, but to even grasp how those forces like mobilize against a threat, I feel like we have to set the stage first. We have to look at the immediate context of human longevity today.
Yeah, because we tend to take it for granted, right?
Yeah.
Average human life expectancy in many countries is sort of, 70 or 80 years?
Easily.
And
Yeah.
people just assume that's because we have, quote-unquote, better doctors now. But that's not the whole story. It's because of this quiet revolution happening behind the scenes.
So what's our roadmap for unpacking this revolution today?
Well, first, I think we have to unpack the foundational sciences of the body, redefine what the body actually is. Then we're going to look at the hidden layers of healthcare, how the mind and machines play into it. And finally, we'll see how all of this is applied to cure the incurable, stop global outbreaks, and literally regrow human body parts.
Regrowing body parts. I can't wait to get to that. But okay, let's start with section 1, redefining medicine and the foundational sciences.
Right, because you have to understand the building blocks of the human body before you can even begin to understand how to fix it.
Which means we have to talk about biology. That's the absolute foundation, right?
It is. Biology explains how cells function, how tissues repair themselves, and crucially, how microorganisms operate. I
Yeah.
mean, bacteria, viruses, fungi. If you don't understand those on a biological level, understanding something like malaria or tuberculosis or, COVID-19 is just literally impossible.
Okay, so if biology is the foundation, what is chemistry doing in the mix?
Well, chemistry is operating at the molecular level. This is something people often forget. Every single bodily process is a chemical reaction.
Really? Like every single one?
Every single one. Digestion, hormone production, muscle contraction, even the electrical signals leaping across your brain synapses, that's all chemistry. It's an endless, chaotic churn of reactions. And medicines are just chemicals. Chemists spend years, sometimes decades, developing and testing safe drugs. Even basic stuff, like paracetamol, aspirin, antibiotics.
Right, so let me see if I can put an analogy to this. If we think of the human body like a house,
Okay, I like that.
biology would be the structural framing, right? Like the wood and the blueprints. And then chemistry is what? It's the plumbing and the electrical wiring running through the walls.
That is exactly right. But if you have a house with framing and wiring, you still need tools to build it and fix it. And that brings us to the power tools of this house analogy, which is physics.
Wait, physics. I don't think most people associate astrophysics or like quantum mechanics with a trip to the emergency room.
No, they don't, but they should.
Mm.
Physics studies matter: energy, motion, forces. And modern diagnostics are essentially just applied physics.
Like X-rays.
X-rays, CT scans, ultrasounds, and especially MRIs. They allow us to see inside the body without ever making a surgical incision.
And it's not just imaging, right? The sources talked about radiation therapy for cancer.
Oh, absolutely. Radiation therapy relies entirely on complex physics to calculate exactly how to precisely target a tumor with ionizing radiation while sparing the healthy tissue around it. It's microscopic ballistics.
That's incredible. And the equipment too, right? Like pacemakers.
Pacemakers, defibrillators, ventilators, all driven by physics. You are manipulating pressure, electricity, and forces to keep the biological system running.
So next time you, the listener, take a basic painkiller for a headache or get an x-ray because you sprained your ankle, you need to realize you aren't just getting a medical diagnosis, you are benefiting from decades of intense chemical and physical research.
Exactly. You're standing on the shoulders of physicists and chemists, not just doctors.
Okay, so that covers the physical foundations, biology, chemistry, physics. But the sources lead us into this whole other realm, which we're calling Section 2, the hidden layers of healthcare.
Right, because we have to move from the physical foundations to the code that programs it all, and the mind that governs it.
Let's start with the code. Genetics. The research says humans have roughly 20,000 genes.
Give or take, yeah. And genetics is how we understand inherited diseases, birth defects, and now highly personalized treatments.
Okay, let me push back on this for a second. Because 20,000 genes sounds like a massive number. But is it just this static blueprint you are born with? Here are your genes, good luck. Or is it an active construction site that medicine can actually intervene in?
That is the million-dollar question. For a long time, we thought it was a read-only document. You got bad code, you were out of luck. But it is absolutely becoming an active construction site. And we'll get into how we actually edit that code later with CRISPR.
Oh, I'm so excited for the CRISPR stuff. But before we get there, there's another hidden layer that blew my mind in these sources. Psychology.
The mind-body connection.
Yes. We used to treat mental health and physical health as totally separate things, right?
Completely segregated. But your mental state, depression, anxiety, trauma, directly, physically impacts your health.
How does that actually work mechanically?
Well, think about chronic stress. It literally rewires your body's chemistry. Long-term stress keeps your cortisol levels elevated, which contributes to high blood pressure, heart disease, sleep disorders.
So a patient's emotional state can literally objectively affect their physical recovery from an illness.
Absolutely. You can have a flawless surgery, but if the patient has severe untreated trauma, their healing process is physically compromised, which is why modern care teams have to be highly interdisciplinary. You can't just have surgeons, you need psychologists too.
Right. And then there's the layer of technology and engineering. AI, wearable tech.
Oh, the tech is exploding. We have AI analyzing medical images, predicting risks before humans even see them, wearable tech monitoring your heart rate and blood oxygen 24/7, telemedicine.
And the engineers building artificial limbs, cochlear implants, dialysis machines, even surgical robots.
It's the total integration of machine and body.
Which brings us perfectly to Section 3, because, okay, we have all these sciences, biology, physics, genetics, psychology, AI, but who is actually operating this massive web?
It requires an army, a highly coordinated army.
Let's look at the professionals making up this army. You've got doctors, obviously.
Right. Doctors act as the diagnosticians and the coordinators. They're like the generals.
But then you have nurses. And the sources were very clear that nurses are the crucial pillar here.
They are the backbone. Daily monitoring, administering the volatile chemicals, and providing that exact emotional support we just talked about, which keeps the patient's stress down.
Then you've got pharmacists. They aren't just counting pills, they're preventing dangerous drug interactions.
Exactly. They are chemical experts. And then researchers creating the breakthroughs, and lab scientists.
Oh, the lab scientists. The sources emphasize this heavily. A single lab scientist analyzing blood or tissue under a microscope. That one result often dictates the entire treatment plan.
It does. It changes the whole trajectory of a patient's life.
Yeah.
And we can't forget public health workers.
Right, the ones protecting populations and preventing outbreaks, which ties into the 4 goals of medicine.
The 4 pillars: prevent, diagnose, treat, and improve quality of life.
Let's walk through an example to show how this army actually works together. Let's use a hypothetical cancer patient.
Okay, good example.
So a patient finds a lump. What happens?
Well, first, biologists have already studied how these cells work. Then, the patient sees the doctor, who orders an MRI.
And the physicists run the MRI.
Exactly. Then a biopsy is taken, and lab scientists test the tissue to confirm it's cancer.
Then geneticists look at the tumor to find the specific mutations driving it.
Right. And once they know the mutation, pharmacists prepare the specific drugs that chemists spent years developing.
While nurses are the ones actually administering the care, and psychologists are helping the patient's mind cope with the trauma of the diagnosis.
And the doctor coordinates that entire symphony.
It's an incredible web of teamwork. But since we just used cancer to illustrate this brilliance, it really begs the biggest question in modern medicine.
Why haven't we cured it yet?
Exactly. With all these brilliant minds working together, why is cancer still so deadly? Which leads us into Section 4. the cancer conundrum?
It's the most complex internal threat the human body faces.
So what is it? Why is it so hard to cure?
Well, first off, the biggest misconception is that cancer is one disease. It isn't. It's over 100 different types. Yeah. Lung, breast, blood, colon, you name it.
Right. And normally our cells follow rules, don't they?
Yes. They grow, they perform their function, and then they undergo programmed cell death. They sacrifice themselves for the good of the body.
But cancer cells, they just ignore those rules.
Completely. They refuse to die, they multiply uncontrollably, and they spread. That spreading is called metastasis.
So let me try an analogy here. Cancer isn't really an outside invader, like a bacteria from a rusty nail. It's more like a rebellion from within your own cells.
That is the perfect way to look at it.
They've forgotten the off switch and just refuse to follow the body's laws. And because they're your cells, your immune system kind of ignores them.
Right, they're wearing the uniform of the home army, which makes it incredibly complicated. Plus, the cancer evolves and mutates constantly. It develops resistance to treatments.
And it often has no early symptoms.
Right. And once it metastasizes, once it spreads to other organs, it becomes a systemic war, not just a local battle.
So how do we fight it? The sources mention a few weapons. Surgery, obviously, to physically remove it.
Yes. And chemotherapy, which is essentially dropping poison into the body to kill anything that's rapidly dividing. But that harms healthy cells too, like hair follicles and stomach lining.
Scorched earth tactics.
Exactly. Then there's radiation, using high-energy physics, and targeted therapy, which goes after those specific genetic mutations we talked about.
But the thing that really stood out in the sources was immunotherapy.
Oh, immunotherapy is fascinating. It's arguably the most exciting frontier in oncology.
Why is that?
Because instead of poisoning the cancer and the rest of the body along with it, scientists are actually teaching the patient's own immune system to recognize and destroy the rebel cells.
Wait, how do they do that? If the cancer is wearing the home team's uniform, how does the immune system see it?
Well, cancer cells often put up this sort of molecular do not attack signal. It foos the immune system. Immunotherapy drugs essentially block that signal. They pull the mask off.
Oh, wow. So suddenly the immune system realizes there's a lethal threat right there.
Right. And it unleashes the body's natural killer cells to dismantle the tumor. It's incredibly elegant.
So does this mean we're close to a single universal cure?
Honestly, no. A single universal cure is highly unlikely just because a brain tumor and a blood cancer operate so differently.
Right, over 100 different diseases.
Exactly. But the future involves detecting it much earlier via AI and using therapies to manage it as a chronic disease rather than an automatic death sentence.
Okay, so cancer is a rebellion from within. But what happens when the threat is an organized invasion from the outside?
When we're talking about pandemics. Section 5.
Right. We are shifting from internal cellular mutations to highly contagious global pathogens. And the sources say we really have to look at the past to understand the future here.
We do. And the benchmark for pandemics is always the Spanish flu of 1918 to 1919.
This part of the research was wild. So the 1918 flu was an H1N1 strain of avian origin. It jumped from birds to humans.
Right. And it infected roughly 500 million people.
Which was a third of the world's population at the time.
Yes. And it killed an estimated 50 to 100 million people.
But the most surprising fact in all of this, it didn't start in Spain.
No, it didn't.
It was first recorded in Camp Funston, Kansas, in the U.S.
Right. But because it was World War I, the nations fighting, the U.S., UK, France, Germany, they censored their press. They didn't want to hurt morale by reporting a plague.
But Spain was neutral.
Exactly. Spain's media reported it freely, so everyone assumed it started there, creating this totally false origin story.
That is crazy. And there was a unique trait to this virus, right? The deadly second wave specifically targeted healthy young adults, like ages 20 to 40.
Yes, and that is terrifying. It killed them because of overactive immune responses called cytokine storms. The virus triggered the immune system so aggressively that it essentially filled the patient's lungs with fluid. Their own strong immune systems drowned them.
Wow. Okay, so fast forward to 2009, the H1N1 swine flu.
Right. It started in Mexico and the U.S. and infected about 20% of the globe.
And the sources called this a genetic remix.
Yes, it was a mix of swine, avian, and human virus strains.
Wait, so the Spanish flu wasn't Spanish, and the swine flu was actually a mix of pig, bird, and human viruses. How do these viruses keep outsmarting us like this?
Through constant evolution. A pig can be infected by a bird virus and a human virus at the same time, and those viruses literally swap genetic code inside the pig, creating a totally new pathogen.
Biological open source coding.
Exactly. But with swine flu, We saw rapid public health coordination. We distributed antivirals like oseltamivir quickly.
Which brings us to COVID-19, 2019 to 2023, SARS-CoV-2.
Spread via airborne droplets. It triggered global lockdowns, accelerated digital medicine, and crucially, led to the historic rapid rollout of mRNA vaccines.
Which is an incredible technological leap. But looking at all three of these, 1918, 2009, 2019, it seems like viruses continuously evolve through animal to human translation.
Inevitable, we can't stop them from emerging.
So what do we do? Just wait for the next one?
No, the experts have outlined 6 primary defenses for the future.
Okay, let's go through them. Defense number 1.
Better surveillance,
Yeah.
an early warning system,
Number 2.
faster vaccines. We did mRNA in months, we need to do it in weeks.
Weeks. Wow. Okay, number 3.
Global cooperation, sharing data and samples transparently across borders, no hiding it.
Number 4.
Strong public health systems. You need the hospitals and labs ready before the surge hits.
Number 5.
AI, using machine learning to predict mutation patterns in viruses before they even jump to humans.
And defense number 6. This one was fascinating.
The One Health approach.
Explain that, because I think it's a profound shift.
It's the recognition that human health, animal health, and environmental health are fundamentally, inextricably linked. If you destroy a forest, you push bats closer to farms, which infects pigs, which infects farmers. You can't protect human health without protecting the ecosystem.
It's all one giant biological reactor. So you listening to this, you lived through COVID-19, but seeing it as part of this historical chain from 1918 shows why scientists are preparing for the next one rather than just reacting to the last one.
Exactly. It's about proactive infrastructure.
Okay, so we've seen how medicine fights rebel cells with cancer and global viral invaders with pandemics. But what happens when a part of the body simply wears out or gets irreparably damaged?
Like a failing heart or kidney.
Yeah, can we just print a new one? Which leads us to section 6, the frontier of regeneration.
This is truly the most futuristic and exciting part of the interdisciplinary frontier, regenerative medicine.
The sources started this section by comparing us to animals, like axolotls.
The little salamanders, yeah. They can regrow entire limbs. Bone, muscle, nerve, everything perfectly. Starfish can regrow arms.
But humans have super limited regeneration.
Very limited. Skin, blood, and the liver. The liver is amazing. It can regrow significant tissue, which is why living people can donate part of their liver.
But why can't we regrow a heart or a leg?
Evolution. Evolution prioritized rapid wound closure over complete regeneration.
Oh, so?
Well, if a primitive human got attacked by a tiger, they needed to stop bleeding immediately, or they'd die. Complex organs require precise blood vessels and nerves to grow slowly. We didn't have time for that. So the body evolved to form scar tissue rapidly.
Ah, okay. So human evolution basically chose the duct tape solution.
That's a great way to put it.
When we get hurt, the body rushes to patch the hole with scar tissue, the duct tape, to stop the bleeding, rather than taking the time to carefully rebuild the original part from scratch like an axolotl does.
Exactly. Scar tissue keeps you alive, but it doesn't function like the original organ. A scarred heart doesn't pump well.
So how is science trying to fix this evolutionary compromise?
Well, the first tool is stem cells.
Right, the blank slate cells.
Yes. They can become heart, nerve, or cartilage tissue under the right conditions. But you need to give them structure.
Which is where tissue engineering and 3D bioprinting come in?
This is where biology meets heavy manufacturing. Scientists use biological scaffolds, living cells, and specialized printers to literally print living tissue.
Like skin and cartilage.
Yes. And eventually the goal is to print kidneys and hearts.
But printing a thick, complex organ like a heart is hard, right?
What?
Because of the blood vessels.
The vascular network is the biggest hurdle. You have to print microscopic capillaries weaving through every millimeter of the organ to keep the inner cells alive, or they suffocate.
That is an insane engineering challenge. But there's another tool here, which might be the ultimate tool, CRISPR.
The ultimate genetic tool, developed by researchers like Jennifer Doudna and Emmanuel Charpentier.
They won the 2020 Nobel Prize for it.
They did.
Wait,
And it was adapted from, of all things, a bacterial immune system.
wait, bacteria have immune systems?
They do. When a virus attacks a bacteria, the bacteria uses CRISPR to take a genetic mugshot of the virus. If it attacks again, it uses a guide RNA to find it, and an enzyme called Cas9 to act as molecular scissors.
It literally cuts the viral DNA.
It cuts the DNA, destroying the virus. And scientists figured out how to program those Cas9 scissors to cut human DNA at exact specific locations.
So we can cut out disease-causing mutations.
Yes, we can correct genetic flaws. It's being used to improve crop drought tolerance, treat genetic diseases, and maybe one day perfect human tissue regeneration, so those printed organs don't get rejected.
That is just, it's mind-blowing. It really
It
is.
changes everything we thought we knew about our own biology.
Which brings us to the end of this incredible journey. We started this deep dive talking about a simple idea. Medicine is just a doctor and a pill.
And we've seen it so much more.
Yeah. It is the brilliant intersection of biology, physics, chemistry, AI, and engineering. We've seen how this unified front is evolving cancer into a manageable condition, building digital shields against the next pandemic, and figuring out how to literally edit our DNA and print new organs.
It's a colossal human achievement.
It is, and I want to leave you, the listener, with a final mind-expanding thought to mull over based on everything we've talked about.
Okay, let's hear it.
If we project this into the future, let's say to the year 2050, if AI is predicting our diseases before we even feel them, if CRISPR is editing out our genetic flaws before we're born, and if 3D bioprinters are replacing our worn-out organs like swapping parts on a car,
Right.
at what point does the human body stop being purely a biological organism and start becoming an engineered system? And if we can swap out our failing parts like a vintage car, what does that mean for our fundamental definition of human health?
That is a question for the next generation of ethicists, I think.
I think so too. Thank you for coming along with us on this deep dive into the source material. Stay insanely curious, and we'll see you next time.